go. So first off, what is the transpose of a matrix? So the transpose is can be defined for any matrix, any. So say M equals, how about M sub 1, 1, M sub 1, 2, M sub 1, 3, and this goes all the way out. M's, you know what, let me not use M, let me use, because you're going to start getting all these darn letters confused. Let's call it A. You guys don't like the same letter being used multiple times. So. Nope, I didn't want to hit that. I want to hit the value. So let's call it A. And then, of course, we have A sub 1, 1, A sub 1, 2, A sub 1, N, and then we have A sub 2, 1, A sub 2, 2. So this is, of course, as you guys know, a little bit of frighteningness. Okay, so what's the transpose say? The transpose says, given any matrix, we could sort of like draw an imaginary line down the diagonal. And basically, we're just going to flip it. That's what it means. Turns out this is a very useful operation on a matrix. So you basically just swap the rows and columns. And so note what this is this is M by N. M rows, N columns. So its transpose is A, and we typically write it with this power T. So what is the transpose? Well, basically what we're going to do is we're going to flip by reflecting over the diagonal. So this would be A sub 1, 1. But then this would be A sub 2, 1, all the way out to, by the way, this is a 1 here. A sub M1, and then this comes down, this would be A sub 1, 2, and this comes all the way down to A sub 1N, and then the diagonal stuff are the same. So again, this definition looks overwhelming, but once we do an example, you'll say, okay, I get it. So again, I would encourage you not to get overwhelmed by all these subscripts and these symbols. Just look at examples. It's not a difficult thing. It's messy to define, but it's not hard to do. Does that make sense? So let's go to the next page real quick, and let's do some examples. So suppose A is this square matrix, 1, 2, 3, 4. What's A sub T? What's its transpose? We'll do it over here. Its transpose, you leave the diagonals alone and you flip-flop the off-diagonal elements. So let's look at another one. How about we do this matrix. What is the transpose of this matrix, which has 2 rows and 3 columns? Well, this one's, again, it's going to be a little, it might not be as obvious to you how to do it if it's not square. So one way to think about it is it's going to be, instead of being 2 rows and 3 columns, it's now going to be 3 rows and 2 columns. And so the first entry is 5, that stays the same. So remember, if you think about it, if the second, think about the definition from the previous page. It says, for example, that if you have your matrix A, and then the second row, or excuse me, second row, second column, let me say that again. First row, second column becomes second row, first column. So then instead of the 8 being there, where should the 8 be? Yeah, so you would say, okay, is the 8 here, right? Okay, so then what happens to the 10? Where does the 10 go? Well, that goes down here. Okay, what about the -3? Where does the -3 go? Say that again. Yeah, but why though? Why? Well, because the -3 was second row, first column. So then it gets transposed to the opposite, which would be first row, second column. Does that make sense? So, you know, you get this. It's a lot more obvious when you have a a square matrix, how this works. But there you go. By the way, if I have, let's say C is equal to, say like 1, say we have a 1 row, how about 5, 10, 15? Well, what's C's transpose? That becomes 5, 10, 15. Does anybody have any questions about this? Comments? Another way to think about this is you take the rows of A and write them as columns. It's another way to think about it, if you want to describe it in English. Any questions about this? Now, it turns out that these matrices, and you know, just to give you a little bit of context, we're not going. This is not a class where we study matrices in depth. But it turns out that you can study the heck out of these matrices, and in many instances, we have matrices that have this special property. We call them symmetric. That is, they're the same thing as their transpose, and those tend to be very important in lots of applications. Some of you will get to see that if you ever take, for example, Calculus 3. You'll learn about, maybe you do remember Calc 3. Some of you had it, and Anthony, you took it. You study this thing of, there's connections between matrices and calculus, for example. And there's this thing called, when you have these things in calculus, some of you know what a derivative is, but you can also have what's called a partial derivative when you start introducing more variables. And in many instances, partial derivatives are symmetric. And for those of you who know what that means, you can think of them in terms of a matrix. So it's very useful. Okay. Anyhow, does this make sense? Does anybody have a question about this? Are you good now, Mackenzie? Does it make more sense now?
Yeah.
Yeah. Yeah, that's fine. All right. Now, another thing that I asked you to define is what's called the inverse. And this is important. You have to have a square matrix for an inverse to exist. So this is analogous to multiplicative inverses. For numbers, for example, what is 5 times 5 inverse? Well, that's the same as 5 times 1/5, which is 1. What is, 2/3 times 2/3 inverse? Well, that's the same as 2/3 times 3/2, which is 1. So numbers have a multiplicative inverse. Not all matrices have one, but we say A does if there is a matrix which will denote A to the minus 1 with A times A to the minus 1 equals I. So you remember we defined this matrix I last class, this what we call the identity matrix. It plays the role of the number 1. So let me just give you a quick little background on why this would be important. All right, on the next page. So, and then we're going to show you that this is a much more complicated idea than a transpose. So let's say, why would we care? So let's consider suppose I wanted to solve this basic equation that I would study as a kid. 3x equals x plus, say, 15. How would I solve this? I would say, okay, this is the same thing as 2x, or excuse me, this is the same as 2x equals 15. And then that implies that 1/2 times 2x is equal to 1/2 times 15. And so we are able to undo what happened to x by taking these inverse operations. And so we get that x is equivalent or equal, excuse me, to 15/2. So here's the analogy. Some of you may So for systems of equations, here's one that you may have studied in a algebra class. Maybe you want to solve 2x plus 4y equals 10 and x minus 5y equals 20. So many of you study equations like this in algebra class, and the first way you're taught to solve it is you take one equation and you solve it for x or y, and then you plug it into the other one, right? And then sometimes they might teach you this little trick where they say, okay, let's conveniently multiply one of these equations by a number, and then we'll add them together, and that eliminated one of the variables. You might remember this. I'm not going to go through it. But it turns out that those are not efficient ways of solving equations. Sure, they're efficient when you have two variables like x and y and two equations, but it's not efficient, say, if I have a real complex problem with, say, hundreds of variables and thousands of equations. So it's easier to rewrite as a matrix problem. Watch how I do this. I'm going to write this as 2, 4, 1, -5 in a matrix. Look at those coefficients. And then using matrix multiplication, this system, these two equations that I have above, can be rewritten as this matrix multiplication equal to this matrix. Now, look at the left-hand side of this board and the right-hand side of this board. The analogy would be if I wanted to solve this matrix equation, if I could just divide through by the matrix, I get what X and Y are. But that doesn't make any sense to divide by a matrix. Think about that. What the hell does that mean? We understand what dividing through by a number means, but think about it. How, do we even have a definition for dividing by a matrix? No, it's in many ways it's meaningless. But if we understand how the algebra problem on the left is actually done, sure, we're usually taught to divide both sides by 2, right? But what are you really doing? What you're really doing is you're multiplying 2x by you're getting rid of that 2 by multiplying by its inverse, which is 1/2. And since numbers, think about this, when we talk about arithmetic of numbers, dividing by 2 is equivalent to multiplying by 1/2. That is true with numbers, but that doesn't make any damn sense with matrices. So the idea is, well, what if this matrix on the left-hand side, this 2, 4, 1, -5, what if there was some other matrix out there that when I multiplied it by 2, 4, 1, -5, it became 1. And if I then multiplied both sides by that, then I could solve the equation. Does that make sense? Turns out you can't always do that, but you can in many cases. And so this is one reason why a matrix inverse would be useful. Now, let me write that on the next page. So we can use shorthand. Or not shorthand, that's a bad word to say. So here's the idea. If, and that's a big if. If, what was the matrix? I already forget. What was it? 2, 4, 1, -5. If 2, 4, 1, -5 has an inverse, we can quote unquote solve for xy by multiplying both sides by the inverse.
Shit. Oh, I was just about to fucking knock. Ew.
Oh my Lord, why are we swearing? There's children in here. All right, this is on the YouTube machine. So what I'm saying is if you multiply both sides by this, then the equation xy, where we multiply 2, 4, 1, -5, then you can write this as the inverse of 2, 4, 1, -5 times, what was it, 10, 20. And then since everything on the right-hand side is just numbers, you get what x and y would have to be. That's the idea. So knowing how to find an inverse of a matrix is a useful thing, if you can. Does anybody have a question about this, a comment? One thing I will say, don't forget, is there's a whole class where you study matrices and this whole idea, in depth. It's called linear algebra. And if you were at a huge university, they have tons and tons of classes where you study these things. And the reason is because they show up everywhere. Matrices are used in all sorts of places, whether it's engineering and physics, or it's chemistry, or it's finance. I mean, think about what Excel is. Microsoft Excel is like a big ass matrix, right? It's what it is. One of the things we do in computers, some of you who've ever had programming, you know this, we store things in arrays. An array is really like a generalized type of matrix where we, instead of storing just numbers, we store maybe words or strings or whatever. You know. Anyhow, that's just my 2 cents on why you should care. For some reason, I always feel like I have to tell you why you should care, even if you don't. All right. So, very good. So on the homework, I said define these things. And so the definition of an inverse is this. any matrix that satisfies this equation. Okay, so then problem 3, I asked you to do some things. So let's go through these real quick, but I don't want to do these two. I'll pick 2 new matrices. How's that sound? So, and you can, I know we've done this, but yeah, absolutely we will. Yeah. But I think it's worth going over this. 3Bs is a good one, all right? So let's say A equals, how about, let's just do 1, 2, 3, 4, because that's easy. And let's say B equals, how about, I don't know, 4, 2, 8, and 4. So I am cautiously writing these numbers down so that I can make a point. What's that? What? I didn't hear what you said. What's that?
Can you not do 4 and 4 like that?
Why? The hell's it matter? So, okay, so you already realized something? What do you realize? What the hell does 4 and 4 have anything to do with it?
We're going to get so confused because it's going to be like flip the diagonal.
No, but you don't flip diagonals for inverses. That's not how an inverse works.
Isn't it?
No.
More than I do.
Well, it depends. Okay. Let me slow down a second. You don't. Okay, that's a good point. If you understand what's happening, good point. Let's use slightly different numbers here. All right, I'm with you. How about? Yeah. Okay, I'm fine. How about? Let's use. All right, settle down. No, we're not using no damn negatives. How about 12 and 3 and 9 and 4? We'll do that. Now there's no confusion, correct? Okay, so the simple stuff is addition and subtraction. So here's the simple ones. And I'll put that, no, I hear you. That was a good point by you, +5. I was very observant. Simple ones. I mean, what is A plus B? A plus B is 13, 6, 12, 7. What is A minus B? Well, that would be -11, -2, -6, 1. So those are simple ones. They don't require anything other than what you would think is obvious. You match the entries, either add them or subtract them. And notice I put simple in quotations. I'm not saying that like a 3rd grader understands this, although they might. This is not, it's just entry to entry. All right, so then now the ones that are sort of, another simple one, for example, would be the transpose of both. Just for fun, what's the transpose of A? It's going to be 1, 3, 2, 4. And the transpose of B is going to be 12, 9, 4, 3. So why do I say these are simple? Because again, they don't require much cognizant ability. I don't think so, at least. So if you know what the definitions are. Oh, that was insulting. It doesn't require much. This is not easy. Relatively speaking, simple. Right? Because as we know, multiplication's tricky. And as maybe, Mackenzie, you figured out, inverses are very tricky. And they don't always exist. I should have asked you, when does it exist? But I actually did. I hinted to that in part B. Yeah, because that's the whole point of this problem is you can't get an inverse of B. Yeah. But you're jumping the gun. We don't know what the hell a determinant is. It is. Well, that's the point. Exactly. We're learning something new. Very good. All right. So next step. Let's do the trickier ones. So what is A times B? Well, A times B is, what was it? 1, 2, 3, 4. I already forget it. And then, what was it? 12, 4, 9, 3. So again, the way I would encourage you to think about multiplication, I'll do this one in detail, and then I'll do the next one quicker. You need to think about it is you have to read left to right. And the reason we're going to make sure you understand that is matrix multiplication, as you should find out in this problem, is not necessarily commutative. 5 times 6 is 30. 6 times 5 is 30. That commutativity we get with multiplication of numbers doesn't always hold for matrices. Very important thing. So anyhow, what you do is you take row, I'm going to take the first row, which is 1, 2, and then I'm going to multiply it by the first column. So when I do that, I get 1 times 12 plus 2 times 9. Now I'll do the first row times the second column, and I get 1 times 4 plus 2 times 3. Now I do the second row times the first column, and I get 3 times 12 plus 4 times 9. 3 times 12, 4 times 9, yeah. First row, first column. Then, excuse me, second row, first column. And then second row, second column. So one of the ways to know if you did it correctly, look at the pattern on the right-hand side. Look how the numbers line up. So that's 30, 10, 36 and 36 is 72, and then 12 and 12 is 24. So again, I told you this last week. I don't know the best way to tell you to learn how to multiply matrices. You just have to practice it until it becomes something you can do. There's luckily for you guys, you have nice videos all over YouTube that can help you with this. I didn't have that when I was learning it. Now, again, notice the pattern, 12, 9, 12, 9, 4, 3, 4, 3, and then you have 1, 2, 1, 2, 3, 4, 3, 4. So there's a nice pattern hidden in there. Does anybody have a question about this? All right, now let's look at B times A. And that's 12, 4, 9, 3 times 1, 2, 3, 4. And first row, first column gives me 12 and 12, which is 24. First row, second column gives me 24 and 16. Well, what's 24 and 16? It's 40. Second row, first column gives me 9 and 9, which is 18. And then 18 and 12 is 30. So the big thing to take from this is AB doesn't equal BA. They're not, or maybe a better way of saying that is, matrix multiplication is not always commutative. All right, so now look, any questions on this before we do the next problem? All right, so here's the inverse part, which is the most difficult. Okay, so two questions. One, does A inverse and B inverse exist? That's the first question. How do you know? And two, what are they? If they exist. Do you understand the problem here? So it's not enough to ask, is there an inverse? It's, if there is, how do we know there is one? And how do we find it? Now, luckily, I shouldn't say luckily, because it's not luck. There's nothing lucky about it. So let me say this. In general, this is a difficult problem. But for 2 by 2, it's doable. And now, how are we going to do it? Well, this, again, sometimes people say, well, this is an unfair question because we didn't know how to begin or what. That was the whole point of me phrasing this problem the way it is. Because here's what's crazy to me about students. Is it's like most students, and I hate to say this about you because you know I love you platonically, of course. Most of you, like I was as a student, are lazy. We want to do the minimal amount of work. You only want to do the problems that you have to turn in. And the problem with math and science is if that's all you do, you ain't learning. You're just not. And so I asked you to find the inverse of A. And then I asked you to, instead of saying, can you find it of B, I said, tell me why you can't. Right? And so what happens is most of you probably went to the internet and found out that there's some nice little cute pattern for the inverse of a 2 by 2 matrix. And that's great. I'm glad you did that. The problem is there's not much learning done there unless you actually try to figure out where that little cute determinant thing comes from that you found, right? So hopefully you will follow along with what I'm going to do here. So let's take A, for example. And what was it? It was 1, 2, 3, 4, right? If, and this is a big thing, if it has an inverse, it must satisfy 1, 2, 3, 4 times, let's call it, let's say this is A, B. I'm not going to use all those subscripts because I don't need them right now because there's only 4 entries. So I'll just use A, B, C, D. Is that fair? Now, what is the definition of an inverse? It must satisfy this. Whoop, that's not very wise of me. It has to equal the 2 by 2 identity matrix. Now, we okay with this? Okay, so that's the definition. So if I don't have anything, I didn't tell us any theorems yet about inverses or anything. There is plenty of theorems out there in the real world. We're not going to talk about them here. So the only thing we have to go on is this. So we need to figure out what numbers, if at all, A, B, and C, and D will make this true. So let's work it out. Do the multiplication. What is the multiplication? Well, on the left-hand side, you get A plus 2C. And then over here, you get B plus 2D. And then you get 3A plus 4C. And then you get 3B plus 4D. Now, we need those numbers, whatever they are, to satisfy this equation. And what's nice about this is even though it looks overwhelming, the right-hand side is very simple. So you can make lots of deductions right away, or lots of conclusions, I should say. So what do we gain from this right away? Well, we gain right away that B and D have a relationship. What is B? Well, B is equal to negative 2D. So if I just look at entry to entry, if they're the same matrices, what do I get right away? I get B is negative 2D. And I get 3A, or excuse me, how about A? I'll solve it completely. I get A is negative 4/3 C. So those are 2 conclusions I can make right away. But I also have to have the other 2 entries on the left-hand side equal the other 2 ones on the right-hand side. Does anybody need to have a question or comment about this? So we can keep going. We also need A to be equal to, what does A also have to equal? It has to equal 1 minus 2C. And then last but not least, B has to equal 1 minus 4D over 3. So I have these four things must be true. Again, where am I getting them from? The first two relationships come from comparing the zeros. The other two come from the entries that have to be equal to 1. So I did a little algebra in my head for the second and the last one. Now, the two ones in the middle tell me right away what A has to be or what C has to be, depending on how you want to solve it. Do you see how I'm reasoning this? Again, I'm looking at the two in the middle. If I take A and replace it in terms of C, I can solve for C, or vice versa. Right? So what I'm saying is if I take these two, if I take this and this, I can determine both A and C. And then if I take this and this, I determine both B and D. Does anybody have a question about that? So let's just do that. So if I have the first one, let's take A, which we know from the previous page on one hand is negative 4/3 C. And on the other hand, we have A equal to 1 minus 2C. Well, replace one of them with the other one. So what this leads to is I have negative 4/3 or 4/3 C must be 1 minus 2C, which is now a one variable algebra problem. I can clear the fraction. That's negative 4C equals 3 minus 6C, which is the same thing as 2C equals 3, which is the same thing as C equals 3/2. So I now found what C is. And now that I know what C is, I get A equals negative 4/3 times 3/2, which simplifies to negative 2. Does anybody have a question about this? Comments? Does anybody think I made a mistake? All right. Now, what you could do if you get brave on this particular problem, you can, instead of doing it for the specific example, you can do it on a generic matrix and you can get a very simple formula. So what I'm going to do is I'm going to stop what I'm doing here and I'm going to say, okay, in general, we can do it on a generic matrix. So we can use these ideas, the above ideas, we can get a formula. Suppose we have A, B, C, D. The inverse of A, B, C, D, like we have, just a generic 2x2 matrix. Its inverse has a very, very simple formula. So if you were paying attention earlier when I chose a B and then Mackenzie said, well, don't do that because it's going to be confusing. The reason that it was going to be confusing is the following. So this thing is equal to 1 over AD minus BC times D negative B negative C A. So you flip the diagonals and then you negate the off diagonal elements. And then you have to multiply it by a number. So let's look at our number, our problem in general. The problem we had was 1, 2, 3, 4. So this is equal to 1. By the way, you should derive this for yourself. I just showed you how to do it in a specific case. This is 1 over 4 minus 6 times 4, negative 2, negative 3, and 1. And if you simplify this, this is negative 2, 1, positive 3/2, and then negative 2, so this would be negative 1/2. And you'll see we got A and C, and that's exactly what we got, negative 2 and 3/2. And if we would have did it for B and D, we would have got the same thing. So I'm going to take a moment here, and then I'm going to describe what I did again, because I don't want you to think that I was not doing the problem for you. But you know the old saying, what do they say? If you give a man a fish, he eats for a day. If you teach a man to fish, they eat for a lifetime. So what I was trying to walk you through in the first couple steps, this idea, if I were to come over here and instead of write 1, 2, 3, 4, if I would have written any other 4 letters, and then I could have went through this, you would get this formula right here. Now this number AD minus BC, it has a special name. It's called the determinant of a matrix. And the reason that's important is because, look, if it's 1 over that and that happens to be 0, guess what? No inverse. Right? You ain't allowed to divide by 0. It doesn't make any sense. So if you go back to when I was choosing my matrix B for an example, 12, 4, 9, 3, notice I chose it just like on the homework. If you take this times this, you get 36. And then if you take this times this, you get 36. So when you subtract them, you get 0. Just like on the homework, I chose it that way. So if we go to the next page, we can make that point. The matrix B, which was, what was it? I already forget. I just wrote the stupid thing down. 12, 4, 9, 3. The matrix 12, 4, 9, 3 does not have an inverse. Why? Because 12 times 3 minus 9 times 4 equals 0. And B inverse, if it existed, would be 1 over 0 times 3, 12, negative 9, negative 4, which is meaningless. Does anybody have a question about this? So if you look at the homework problem, the matrix B I chose had a determinant of 0 as well. 30 minus 30 is 0. By the way, you guys use something every day that is a very, very complex problems in what we call a matrix, or what we call, the fancy word for it is what's called an eigenvalue problem. But anytime you use a Google search engine, this is exactly what it's doing. It's solving this big, scary matrix equation. That's how it page ranks. So, not that you care about it, but I thought I'd share. So, turns out that solving systems of equations is very difficult, not just for humans, but also for computers. It's really, it's some of you who know if you know anything about programming and things like the number of steps it takes to get a task done. In general, solving systems of equations is difficult. So we invent better ways than what we're doing here, and it's, or more efficient ways, I should say. So it's a big area of modern research to this day. If you're interested in it. Okay. Any other questions? Problem 4 is if you just multiply C to itself a couple times, you'll see there's a pattern. A very simple pattern for powers of diagonal matrices. So a matrix that has numbers only on the diagonal is called a diagonal matrix. And it turns out that powers of diagonals are very, very, they're very easy to compute. Now, that's not the case in general for matrices. If I just gave you the matrix 1, 2, 3, 4 and asked you to take that matrix to the power 10, it would be very painful for you. But this one is not. Does anybody have a question, comment, concern? Supposed to say yes already. I'm super annoyed. All right. All righty. Okay, so what's next then? Where are we going from here? Well, we're going to move away from matrices, at least for the time being. So the next thing we're going to do is we're going to talk about the math that's used to analyze something that is near and dear to you computer science majors, and that is algorithms. So what's next is how to analyze algorithms. And so for those of us who have, every one of us has undoubtedly heard the word algorithm before in many different contexts. What is the definition of an algorithm? And more importantly, you guys have used algorithms over and over in your life since the first time you learned how to do addition and subtraction in school. Those things you learned for like multiplying 2- and 3-digit numbers, and you remember you're carrying ones and putting zeros places you had no idea what you're doing, and then long division, those are algorithms.
Wait, it's 11 now, but
All right, so the way that like most textbooks, and I think our textbook does this similarly. So let's define it. So an algorithm is, and this is important, a finite sequence of instructions for computing or for solving a problem. So again, what you learned in elementary school about multiplying and dividing integers, those are algorithms. Long division is an algorithm. What you learned in calculus about computing derivatives, that's an algorithm. But there's also problems that computers can solve for us that we might not think of from math's points of view. Like, for example, if I go to a vending machine and I put money in and then I hit a button, well, there's this precise set of instructions that whatever I push on there, the vending machine's computer knows what to do in order to give you what you ask for. Or I might have a list of names in an Excel spreadsheet and I want to put them in alphabetical order. How do you do that? If I have a bunch of numbers, how do I write computer code to find all the even numbers? So there's all kinds of different algorithms. And one of the things we'd like to know is, if I have an algorithm that's designed to solve a problem or do a computation, one thing we might ask is, how many steps should it take? So one way we think about this is, what is the cost of this algorithm? How much time and sort of energy does it take? You know, like I don't know if you guys think about it this way, but like if I come up here and touch my computer, it is blazing hot right now because there is all kinds of crap happening. My camera's running. I am writing on a whiteboard. There's all kinds of things happening. And my computer is using a ton of energy right now, I guess, relatively speaking. And if I were to start opening more windows and doing more tasks, my computer, you know, most humans don't really think about how much of your processor or what percentage is running or what speed, but that stuff matters. So what we'd like to do is we would like to get sort of a basic understanding of how we might analyze these things. For example, if I wanted to teach a computer to multiply matrices because it's not fun to do by hand, how many computations is it going to take the computer to do it? If I want to teach a computer to take take a matrix and compute its inverse, because that is hard to do by hand. It's not easy to do by hand. And if I want to teach a computer to do, how many steps is it going to take? Is it going to take 5 computations? Is it going to take 50? We would imagine that a 2 by 2 matrix takes less steps than a 10 by 10. But how much more? How many more steps? So we'd like to quantify this, and the basic name for all this is analyzing algorithms. And some of you will take a class. I think algorithm analysis is a class that most computer science students must take. Any questions? Like, so a good exercise for you to understand how algorithms is take your little time machine in your brain and go back and write down an algorithm for doing long division. Think about that. Could you write in English, you know, what sometimes we call this pseudocode? Can you write code that takes a number, then takes another number and divides it? Now, you knew how to do it from memorization as a kid because you did it repetitively. But how would you write down those instructions? Okay. Does anybody have a question or a comment about this? Who are they named after?
Yeah.
It's usually, what's his name? The guy who first wrote the first algebra. El Khwarizmi, I think was his name. Yeah, so right. So the first algebra book, which is like in 800s or something, I think it's named after that. And it comes, that's where algebra comes from too, because it comes from the idea of like, you know, it's very interesting. I think it's El Khwarizmi is how you say his name. You could Google it.
I thought it was the U.S. senator.
Yeah. Well, wasn't the one senator, was it like 2 years ago, some loony like Republican from Indiana or something, said something that like, something to the effect that the Western world created all of like math and science or something ridiculous. And everybody was like, well, wait a second. Or no, he said something to the fact that I would never use a number system made up by like from someone from the Arab world or something. Meanwhile, the integers we use every day they're literally called the Hindu Arabic numerals. That's what we use every single day. People are stupid, but we already knew that, right? We already knew people were stupid. All right, so how do we do this? How do we analyze algorithms? So let's sort of set the stage for this. I should think of it this way instead. So one way to analyze an algorithm is to study and quantify how long it takes to complete a task. So, for example, I could say to you, multiply these 2-digit numbers together, and then 3-digit number together. And you could think about how many steps it takes you to do the 2x2 numbers, and then the 3-digit numbers by 3-digit numbers, etc. And you could come up with some pattern, some function that describes how long it takes. And then if we know that a computer, each one of those steps takes a certain amount of time, then we could figure out how long it's going to take the computer to complete the total task. If you're ever curious about this, there was a big deal just like a year or so ago. These scientists figured out a more efficient way for computers to multiply, which you might think is ridiculous. But then again, most of us never even think about how a calculator works. But if you're ever bored and you want to kill some time, ask yourself, how do computers multiply? You might be surprised how they do it.
Of course. The guy that wrote Doom, that was his kind of claim to fame, is a faster algorithm for square roots.
And that's important too. I mean, that's a great point. These algorithms, if you ever wondered why video games look different now than they did 20 years ago, how do these movies like Toy Story, how do they look so much more realistic than they did 20, 25 years ago? It comes down to things like that. How do you refine and how do you do these computations quickly enough so that we can animate and it looks realistic? It's quite fascinating. The Doom guy. There was just a big thing about Doom a couple days ago, or maybe a couple weeks ago. Wasn't like the anniversary of it or something like that?
I remember Facebook now working on the virtual reality goggles.
Oh, really?
And he's also independent as well.
Well, I would imagine so.
I think his other side project is making rocket.
Helps to be smart. Okay, so the first thing we're going to do is talk about how we can do this. So it turns out, is that his name?
Do you ever want to do more than speaking?
Did I ever want to? Yeah, it's a good question. I thought about it. Yeah, but I like this lifestyle. It's different. Like, I mean, I've thought about doing other things. I don't know. I've told you this before. I think sometimes you got to figure out what your best skills are. And it's hard to figure that out, I think, for some people. But you got to figure out, what do you think you're better at than other people? And then you just run with it. So I always thought you have to get good at something. And I took job interviews at banks and stuff like that before I came here. in other things, and this is more appealing to me. Who knows though? Maybe I'll leave here and go work at PNC or something, or some financial company. I don't know. Yeah, I don't know. It's interesting. I could never teach like in a school, but being able to like, I couldn't do like high school. I'd lose my mind. But I like math. I like learning things. I like being able to do math like as part of my job. Yeah. So I think I was lucky to end up getting this job, because typically it's hard to get an academic job for one. They're not easy to get. And not even that, it's not easy to get one where you want to be. Like I didn't want to leave Pittsburgh, so it was dumb luck they happened to be hiring when I was finishing school. You know, most people, my friends from graduate school, are all over the country working. The ones that stayed in academia. And then others, there's other, I mean, there's tons of jobs. They're not.
If you ever wanted to like leave.
Leave what? Working at LaRoche?
No, like being a professional.
No, but it's a good lifestyle. The only negative to this lifestyle is that there's more money to be had in the industry. Like, so what I mean by that is if I went and worked at PNC Bank, I would absolutely make more money. But but it ain't that, it's not that much more money, right? And then you also, here's another thing that's a good piece of advice for you guys when you're finishing school and getting jobs, is you have to, and I got a buddy, we talk about this all the time, you got to think about your quality of life. A lot of people think that money is the most important thing, and money, trust me, it solves. A lot of people say money don't solve problems. Oh yes, it solves pretty much everything, right? Yeah, right. The only people who say money don't buy happiness, that's what my dad used to say, people that ain't got money, right? Trust me, money helps solve lots of problems, but it's not like the way this place works. I mean, it's not like, you know, I'm not going to drive a Bentley, I don't think, working here, but I don't do that bad. And this is the kind of job too, where you can do things, you can make it work for you financially, or you could just come in and do the minimum and just, you know, whatever. Yeah, do you know where?
In Minneapolis.
Yeah. See, another thing too that makes this job very stress-free. Many university jobs have what's called tenure. And what tenure means is once you get your tenure, you're pretty much set for life. Now, at most places, that requires that you have most places it's not easy to get tenure anymore, particularly. And also it's very stressful because you have to do lots of things well. You have to be very much adept at research and publishing papers, and not just publishing papers, but you have to publish in reputable journals. So particularly in the sciences, you know, that's a very stressful time. Whereas here, we don't value that the same way we value teaching. Like teaching is held as the #1 priority here, and advising and stuff. So I don't have the stress that maybe other people have as far as I'm not publishing enough or I'm not doing those things. And we don't technically have tenure in that sense. We have contracts where your job is secure for a very long time, but we don't call it tenure here. So, you know, it's just one of those, again, like I was saying, quality of life is such an important thing. Like here is stress levels are very low for me, and I make my own hours, right? A lot of people don't get to do that. I take my kid to school, I come in here. Now that said, I mean, I could go get, like I said, I go downtown and take a certain job and I'd probably, you know, make more money, but it would not be probably as stress-free. And I'm not saying this job's stress-free because I'm annoyed right now with making schedules. There's stuff that annoys me, but it ain't the same annoyances that maybe other people have, right? And it's fun to teach this stuff. I do, like, I feel like I'm pretty good at teaching this. I don't want to say I'm great at it. I don't know. Most of you guys might say whatever, but I feel like there's a shortage in particular of people who can make stuff like this a little easier to learn. This is hard stuff to learn. I also think, like with calculus, I love teaching calculus because so many students want to get into the sciences and then they end up hating it and switch because of how difficult calculus is typically made. And that's at most schools, not all schools, but a lot of schools. And I'd like to maybe be the person who makes that opposite. Maybe people don't like move out and find a new major because they might find something they enjoy, or it's not as painful as it could have been. So I don't know. I mean, I teach Calc 1 and 2 every semester for that reason. I don't have to. I like to do it. Anyhow, yeah. So I don't know. I haven't thought about it. It'd be different. Like, I mean, Amy and I've been with my wife. We just had our 9th wedding anniversary. We've been together since like 2004. She already had a job, so I wasn't going anywhere. So it was like dumb luck I had. They wanted to hire me here, and I'm like, I think we fit each other good. I don't know. What do you think?
You teach Calc 3 too?
I have, not this semester though. You missed it. Last year I did.
Next semester?
Not next semester, no. I don't know. I'm taking differential equations. You have to take that anyhow.
Oh, yeah.
Should all take that class. That's a fun class.
What's the prerequisite for that?
Well, you should have Calc 3, but we're waiving that for most students this semester because we had to cancel Calc 3 in the fall when we normally would have run it this semester. We had to cancel because we had an instructor shortage, and I couldn't teach every class. So, but anyhow, if you want to take it and you've had at least Calc 2, then it should not be an issue. I mean, if you've only had Calc 1, you could. I wouldn't necessarily recommend it because there's a lot of stuff in Calc 2 that are useful there, but it's a good class. Differential equations is a cool class because it's one of the first times you really get to see why they made you learn all this calculus. That's the place where it's finally, you don't realize it in physics, but in physics, you're like, hey, calculus is important. But most of you go to physics class and forget, did you even learn calculus? Dr. Cho yells at me. He said, why can't they do derivatives and integrals? And I'm like, I don't know. Right? But once you get to differential equations, you really see these applications and what calculus can help us solve, real world type stuff. In Calc 1 and 2, we do a lot of baby examples of things, but you really start to see it in differential equation. And as I've said before, that's the language of science. I mean, you look around you, things are changing. That's what differential equations is about. Anyhow, look, we get off topic. I love this. We get off topic every class. It's so great.
We have not.
No, I know I feel bad for those of you who've never got to enjoy the excitement of a semester with me, because you're missing out.
Like Friday lab for Calc 2.
Those are fun, yeah. Good old days. You had the summer with me at first, right?
Yeah.
Yeah. See, that even summer's even more fun because I'm in a much more exciting zone in the summer.
It was like 3-hour class, right?
Yeah, that was brutal. All right, let's wrap this up real quick. We're out of time, but that's a good question. And I'm always happy to answer questions like that. People ask me that all the time. Why don't you go make more money? I'm like, I ain't poor. Got a nice car. I got a nice house. Although Amy keeps wanting to get a bigger house. I keep ignoring it. And then she's a teacher. She got the good health benefits. What else do you need in life?
Yeah, isn't she 5th grade?
She's a 5th grade. God bless her and the rest of them. I don't know how they do it. Okay, so here's what we're going to talk about next is we can use functions to do this. So one definition we have to make before we go is the following. So here's a scary thing. So let f and g be functions from, say, the integers into the real numbers. So we say, and this is going to seem kind of like in the middle of nowhere right now, but we say f of x is big O of g of x if there are constants c and k such that the absolute value of f of x is less than or equal to this constant c times the absolute value of g of x when x is larger than k. So this is a loaded definition. And by the way, let me remind or just write this down what this means. So this reads f of x is big O of g of x. Maybe I should put big O like OHO. So that's the way you read that. And so before we leave, let's just think about what this is kind of measuring. What this is measuring how, think about what it's measuring. It's measuring the steepness of, say, the graph of f and comparing it to the graph of g. Is one way to think about this. What is happening, as we read left to right on these functions? What is their growth rate? We're measuring how they grow. So we're relating the function f and g with how they grow. So this is a good way of measuring or quantifying growth rate. And we'll talk more about this on Wednesday. And by the way, you can Google big O notation. You'll learn a lot. Anyhow, thank you guys. I appreciate it. If you ever have questions you want to ask me, feel free to ask me. I don't mind answering real life questions either. So please schedule and get registered for the spring. Reach out to me and your advisor. All right, everybody. Thank you very much. Bye now.